All right. So we're going to start with an introduction to virtual machines. This material is from an old book by Smith and Nair from back in 2003, but then I've also updated it with more materials. The first chapter of that book, from which most of this material comes, it's available for free online, and it's also linked from the course website. There's also useful material in Andrew Tenenbaum's book, Chapter 7. So the material is from many sources, but the primary reference is the Smith and Nair's book, Virtual Machines, Chapter 1. All right. So what is virtualization? Here, you can take, as the name suggests, you can take any physical resource and make it appear as if these are many virtual resources. Okay, so for example, for virtualization, for example, you could take like a single physical disk, like we saw in the case of RAID. That was a special type of virtualization where we took many physical disks and made it appear like a single virtual disk, right? And then with added properties of fault tolerance, parallelism, and so forth. So likewise, you could take a single physical disk and make it appear like multiple virtual disks. So that's a one-to-many virtualization. Or you could take like a single network interface card and make it appear like multiple virtual network interface cards. So, and likewise, you can do the same thing for an entire computer, right? You can take a single physical computer and make it look like many virtual computers, each of which runs its own operating system and has, it looks like completely like a physical computer, but you don't know it when you use it as a user, that it's a software representation of a physical computer. So that's a general idea behind, very broad idea of virtualization. So there's one-to-many virtualization, where one physical resource is made to appear like many virtual resources, and many-to-one virtualization, where many physical resources are made to appear like a single virtual resource. And of course, many-to-many, all combinations. So many physical resources can be made to look like many virtual resources. So there's a question, is that like machines we used for the last assignment? Yes. So in your assignment 2, you were logging into a machine using SSH, and you had full root access, and you could install any software in those machines. You can install kernel modules, you can do anything you wanted with it, right? But you did not have like a dedicated, there were not 84 physical machines out there in some room. These were virtual machines, and they were running on a common set of physical machines. Specifically, they were VMware virtual machines. And although you didn't see, unless you log in through a VMware console, then you may realize that, oh, this is a VMware virtual machine. But if you didn't do that, if you just access it through SSH, then you wouldn't realize that it's a virtual machine that's sharing the physical resources with others. So again, that's an example of one-to-many virtualization. Okay. So here's the example of the virtual disk that I gave, and this is just one very naive way of implementing disk virtualization, specifically one-to-many disk virtualization. So you have a real physical disk on which we are trying to give the illusion of having two virtual disks. And the way to do that is by using a combination of abstractions and interfaces. So what that means is that we have the operating system, which manages the real physical disk. It provides a system call interface, which is the first line above the real disk, right? So using that system call interface, you can create two files, file 1 and file 2, using, say, open system call, right? And then now, once you have these files created, you can then write another piece of software, which is a virtualization layer, which provides you an abstraction of a virtual disk on top of a physical disk, which is a file, right? So, so we have taken the abstraction of a file and then implemented another software that makes it appear like a virtual disk. And if there is another software that uses virtual disk 1 or virtual disk 2 to that software, it will look like these virtual disks are real physical disks. They'll have the same properties as a real physical disk. But actually any IO operations on these virtual disks will go through these intermediate layers and be shared or multiplexed on the real disk at the very bottom. Any questions so far? All right. So, so we are now going to take this idea of this storage virtualization that we saw earlier and move it to disk virtualization, which is to a virtual machine. All right. So, so as I mentioned earlier, for a virtual machine, we are taking an entire physical computer and preparing a software representation of a physical computer. So what does a physical computer consist of? Mainly three resources: CPU, memory, and IO devices. Right? So there can be many different types of IO devices, but broadly we can classify all the IO devices under one umbrella. So CPU, memory, and IO. And if we can virtualize these three resources, CPU, memory, and IO, then we have a software representation of a physical machine, or that's a virtual machine. Okay. So why would we want to do something like this, first of all? Like, why is this a good idea? It turns out that besides just being cool, there are many practical use cases. For example, you have a physical computer and, traditionally we run one operating system on it, say Mac OS or, Windows or Linux. But then what if we wanted two different operating systems, but running side by side, like not one or the other, but rather side by side at the same time. So then you can use something like a virtualization. You can have multiple virtual machines, each of them running different operating system. And underneath there could be a virtualization layer, which manages and multiplexes the hardware between different operating systems. Okay, so that's like the very first use case people encounter when they become familiar with virtual machines. But there are more compelling, deeper applications. One of them is isolation, which means that, let's say you want to run two different applications and you want them to share a physical machine, but you don't want one application to interfere with another application, right? So you don't want one application to see the memory of another application or probe what processes are running, and so forth, or hog up certain resources at the expense of the other application. So virtual machines provide a stronger isolation boundary than traditional processes. So if you're running two different applications, two different VMs, then one application won't even be aware that there's another application running on the same machine. So it's a stronger form of isolation. And then likewise, there are applications for security. You download some software from the internet and you want to run it on your machine, but you don't trust the software. So what can you do? You can put it in a virtual machine like a box and let it run in a VM. So the application thinks that it's running on a real machine, but actually it's running in a VM. So if it does something bad, like compromise the VM, then you can simply throw away the compromised VM. You don't have your original host system will not be compromised by untrusted software, right? So it's called sandboxing environment. Sandbox means you run something in a protected environment that cannot harm the outside environment. We will talk more about other applications like live migration, means moving a VM from one machine, physical machine, to another physical machine without turning it off. People often use VMs for testing and development. This is very common, like you want to test some piece of software, and then you don't have all the different hardware types available in front of you, so you can create virtualized environments, and then you can do testing on these virtualized environments. There's a question from Gaurav. It's asking, is having multiple users on one OS using it at the same time a kind of virtualization? So the question is, if you have multiple users in a single OS and you all log in, like you all log into remote.cs and then you're all running your processes side by side, is that virtualization? It's not virtualization. I mean, each of you gets a shell into which you log in and you run your processes, but you're not running within a VM. So so you kind of get an execution environment, a shell, where you can enter commands and you can even observe other people's processes. So so it's not really virtualization in the traditional sense. You could, you know, we will talk later about containers and process VMs. So there we kind of start approaching a truer form of virtualization, but they're certainly not virtual machines. Okay. There's another question: is dual booting with different OSs on a single machine the same as virtualization? What is the difference? So so dual booting refers to like when you on your hard disk you create two partitions, and then you install to different operating systems and different partitions. So when you boot power on your machine, it will give you a choice. Do you have Windows and Linux? Do you want to log into Windows or do you want to log into Linux, right? And then you pick one. And then once you pick one of them, the machine will boot into that OS, all right? But once you're booted into an OS, you're stuck with that. You can't go back and run Windows also at the same time, right? For that, you have to reboot your machine all over. So dual booting is not the same as virtualization. That's running dual booting means like you at boot time you pick one OS and then that OS runs natively. Natively means like it has direct control of the hardware. So no, dual booting is not virtualization because those multiple OSs are not running side by side at the same time. You can boot a machine into different operating systems, but you can't run them both at the same time. All right. Any other questions so far? All right. So also there are some interesting use cases for virtualization. For example, you might have instructions that are, for example, we know there's like x86 ISA or PowerPC ISA or ARM processors. These are provided by specific CPUs, and you can kind of run an OS on top of these CPUs, and it will just work fine. You can compile and run applications on these ISAs. But sometimes people come up with imaginary ISAs, and there are no physical CPUs available that support those ISAs, but they want to run applications against these imaginary ISAs. And for that, you could create a virtual machine that provides an imaginary ISA. For example, Java virtual machine that you might be familiar with, where you write your Java program and you run it. You use .class files, you run them, and you run it inside an interpreted environment, which is a Java JVM. So JVM provides a bytecode ISA, and you can't go out and buy a CPU that provides you bytecode ISA. Rather, you have to run it within a VM that uses bytecode ISA. All right. So that's so those kind of cool things are possible. There's a question from Harshit, how is sandboxing different from containerization? And it depends. Sandboxing is a very loose term, but generally it means that you're running some untrusted application and you want to limit its capabilities. So sandboxing, you can limit the capabilities of application or process in different ways. And that's what sandboxing refers to. But you can limit its capabilities through a container. Container provides like a virtualization of various resources that a processes or a group of processes can access and what they can do, but it's not necessarily only for limiting an application. You can use containerization for various things, but one of the applications of containerization could be sandboxing. Okay, so we'll have another lecture on containers where we will discuss these in greater detail. Okay, so these are some of the use cases, right? So now we will go down further and look at one of the earlier pictures that we had started the class with, right? So this interfaces of a computer system, because it's really important to understand the interfaces of a computer system to understand what different virtualization mechanisms are doing. So if you remember this picture, we had this line in the middle, which is marked 7 and 8, is the ISA interface, instruction set architecture. So everything below this line is hardware, and everything above that line is software, right? So this line, instruction set architecture, is the set of instructions that are provided by the processor, the CPU, to all the software applications and the OS that runs on top of it. And then within that, there's a classification of user ISA and system ISA. So user ISA here refers to the set of instructions that user space applications can execute, whereas system ISA refers to the set of instructions that only the operating system can execute. So, or the most privileged software can execute. So between 7 and 8 taken together defines the complete instruction set architecture. All right, and we'll see why this distinction between user ISA and system ISA is important. And then there is another important interface we want to recap here, the system call interface, which is marked number 3. And as we all know, system calls are special requests from application programs that want the operating system to do something on their behalf, like opening a file, reading and writing to IO devices, sending network packets or receiving packets, and so forth. Okay, so just remember these interfaces, 3, 7, and 8. 7 and 8 together are called the instruction set architecture, whereas 3 is the system call interface. And we had learned about this combination, which is ABI, or Application Binary Interface. And this refers to the combination of interfaces 3 and 7. So if you notice, interface 3 is system call, and then the interface 7 is the user ISA interface, the set of instructions that applications can execute without intervention by the OS. So why is this important? 3 plus 7, the ABI, because ABI is the view of the underlying machine that's seen by user space application. So if you see a user space application, what is it doing? Ordinarily, when it doesn't need any special services, it will be executing user ISA instructions. And then when it needs special services, then it will make system calls. Actually, system calls are also invoked through special type of instructions called the sysenter instruction. On Intel CPUs, on x86 CPUs, there's a sysenter instruction which is used to invoke a system call. So, so either you're invoking a system call or you're executing user ISA instructions. So that's the view of the underlying world as seen by user space application. So this is important because depending on what interface we are virtualizing, the ISA interface or the ABI interface, then we can get different kinds of virtual machines, all right? So in one case, we get a system virtual machine. In another case, we get a process virtual machine. So any questions so far about this API and interface? Anything that's not clear? All right, so there's a question from Aditya. Does interface 7 give direct access to execution hardware to user level application? Is there any supervision there? So by definition, user ISA instructions means that these are non-privileged instructions. They're normal instructions. For example, adding two numbers or floating point operations, or loading and storing to memory region, load store operations to a process's own memory address space. Right? So these are normal instructions. To do these instructions, the application can't do anything wrong. So it would just, it can directly issue those instructions to the CPU. CPU will simply execute those instructions. Any memory access checks, for example, are performed in hardware by the MMU. So there's no involvement of operating system in these instructions. Only time the OS gets involved is when the application makes system call. So when a syscall instruction is executed, then it automatically transfers control to the OS. Likewise, if any user ISA instruction causes an exception, like you do dereference and null pointer, or you do divide by zero and floating point, so those exceptions would then transfer control to the OS. But they're not system calls, they're exceptions. So normally there is no supervision as long as the application isn't doing something strange. Okay. Does that answer your question? Okay. So another question is, or rather a comment, I think, x86 should use syscall instruction or sysenter. Since sysenter was legacy style, you can also invoke syscall through VDSO interface without using syscall instruction. Well, that's only partially correct. I mean, VDSO is just a faster way of passing parameters down to the OS, but you can't, to invoke a syscall, you still need the sysenter instruction. So with sysenter instruction, you can invoke the sysenter instruction, but to pass parameters, you can use the VDSO interface, but we won't get into it here right now. Okay, any other questions? All right, so let's go to the next slide. So as I had hinted in the previous slide, there are two types of VMs, process VMs and system VMs. And this depend upon what interface we are virtualizing. So if we take the ABI, so if you look at this picture for next to process VM, there is an application process running, and it's running on top of virtualization software. So what's the virtualization software doing? It is hiding the ABI of the underlying host system. So the host system consists of the hardware, the CPU, memory, IO devices, and then the OS, right? So normally application process would see the system call interface plus user ISA. But if we hide this ABI by writing a virtualization software, so what that means is that whenever application runs, it's running against an interface provided by the virtualization software. And the virtualization software gets to decide how the ABI appears to the user level application. So what it's effectively doing is it's virtualizing the view of the world seen by this user level application. Okay, so this is called a process VM because we're taking a single process or maybe a group of processes and hiding their view of the rest of the world seen by these processes. So a common application, a common use case is, like I mentioned, Java virtual machine, where applications are written against a special virtual ISA called the bytecode. And then they are compiled and they compile into a bytecode. And when you run them, the virtualization software called JVM, it takes every single instruction in the bytecode and then converts them to the underlying system call and user ISA interfaces, depending on what the application is trying to do. So as far as the application is concerned, it sees only the interface that's exposed by the virtualization software, but underneath the virtualization software may be transforming those operations into the lower level ABI. Okay, then we'll see what this might be useful for in a little bit. And although the picture shows as if the virtualization software is hiding the entire ABI, that doesn't have to be the case. For example, virtualization software may hide only part of the ABI. For example, you may only hide the system calls, or you may only hide the user ISA, or you may only hide part of both. So there's a wide latitude in what you can do, and that can give you different types of process VMs as well. Okay, and another property of process virtual machines is that they terminate when the guest process terminates. So what that means is this virtualization software exists only as long as the application process exists. And then once the application process dies, then the virtualization software also would terminate. Again, going back to the example of Java applications, the JVM, Java Virtual Machine software, it starts when you start running a Java program. Then once your Java program terminates, the JVM software also dies. Okay. Likewise, we have the second category of virtual machines is system VMs, where we are virtualizing the ISA interface. So what that means is that from the hardware, from the CPU especially, we get this instruction set architecture ISA interface. Then you can run a virtualization software that directly controls the hardware. And this virtualization software can then provide a virtual ISA in the sense that it's a transformed ISA that may be slightly different from the native ISA of the underlying machine. And on top of that virtual ISA, you can run an OS and entire applications, right? So, what that means is that you can basically run an entire software stack on top of this virtualized ISA provided by the system VM. Okay, so the view of the world seen by the OS plus its applications is the interface exposed by the virtual machine. And whenever the OS or applications do something that the virtualization software wants to transform or emulate, then you trap into the virtualization software, which then transforms them into the underlying hardware. So this is a very high level overview of the differences between the two types of VM. So one thing I must mention is that the process VM is also called a runtime. So you will often hear the term runtime. And runtime is has a very specific technical meaning, which is that you refer to a process VM, like a Java virtual machine, all right? And what that means is that this runtime exists only as long as the application is running, and it dies when the application dies. Okay. Of course, this is a very strict definition of a runtime. There may be some runtimes which continue running even though the application dies, but in a strict technical sense, runtimes are only last as long as the application runs. In the case of system VMs, the virtualization software is called the hypervisor. Sometimes it's also called the virtual machine monitor, or VMM, but they mean the same thing. And we'll discuss each of these in a little more detail. We'll talk about system VMs in more detail and process VMs in a little less detail. Okay, any other questions so far? Yeah, Shengdong has a comment, there are no zero cost abstractions. Yes, like anytime you're adding another layer of software, we can always solve a problem, but there is always a cost to it. So there's a cost versus functionality trade-off involved. in every layer of virtualization. Okay, any other questions? Sorry, I missed the question from Satrio. Does the performance deteriorate if we use virtual machine? Yes, the trick is to keep the cost minimum, because if the performance is terrible, then virtual machines are no good, right? So, but then they open up a lot of new functionality. So when, of course, virtual machines were very old, from 1970s. IBM had virtual machines with very extensive hardware software support in its IBM mainframe systems. But then, kind of people forgot about those VMs, and then in towards the end of 1990s, VMware revived that idea, and it figured out a way to run VMs on x86 systems. Now that by itself wasn't new. I mean, you could always run very slow VMs, but what VMware figured out was to run it faster than what others could do, using a very cool technique called binary patching and dynamic binary patching. So that really gave VMware a head start. But the point is that even with VMware's initial technique of dynamic binary patching, they can only get 70% of the native hardware speed. So if you ran a VM in VMware environment back then, that is at the very beginning when VMware started, you could only get 70% of the hardware performance. That was still better than the other solutions, but that 30% was the cost. And some people were willing to pay that 30% cost in order to run a VM. Okay, but of course, over time, it has improved, and now you can, depending on how you configure your VM, you can get almost near native or bare metal performance in a VM. Okay, also depends on what you're doing inside a VM, but it's not uncommon to get close to bare metal performance. Okay, so we'll do kind of a one slide coverage of process virtual machines, and then we will move on to system virtual machines, which is the main focus of this course. Right. So as we discussed earlier, virtual machines are associated with a single application, a single user space application. And we've already seen an example of process virtual machine, which is the idea of a process. Right? What is a process? The very first concept that we learned in this class, like you load your program into the memory, and then you make the program believe that it has its own memory, its own dedicated memory, right? So that's that dedicated memory is called the virtual address space. Okay, so we talked about virtual memory earlier, right? And then there is the physical. So each process can have its own virtual memory, and each virtual memory, they're multiplexed together in the physical memory. And then each process also gets its own virtual CPU. What does that mean? Like you get a thread of execution, and the process believes it's executing its own instructions one by one without interference by any other process. But of course, underneath that, OS can preempt a process and schedule another process, switch back and forth between them, and so on. Okay. Then so that CPU memory virtualized, and then for IO accesses, processors are given the notion of a file system where you can create files and so on. So you have storage virtualization, memory virtualization, and in a way CPU virtualization. So you can think of the notion of a process as a runtime that's provided by the underlying operating system. Then there's another category of virtual process VMs called the emulators. So what that means is that you can run a program that was compiled for one instruction set architecture or one ABI on top of another system that has a different ABI, right? So so what does that mean? For example, let's say I compile a program for x86 CPUs, but then now I have an ARM CPU. If I just have the binary and not the source code, then I can't recompile the application. Then I can't just run it on the ARM CPU, right? It's an x86 application. How can I run it on ARM CPU? Well, you can if you have a runtime that converts the x86 ISA into the ARM ISA, right? So you can read each x86 instruction, convert it to the ARM instruction, and run the equivalent instruction. So you have to be very careful in doing that to maintain the semantics of the application, but that's doable. So that's an emulation, like converting from one ISA to another ISA, emulating from one ISA to another ISA. So an example of this is shown here in the picture. It's called the Digital FX32 emulator, right? So that's kind of a fancy name. What that meant was, like, back in the 90s, 1990s, Microsoft was very popular, right? And its operating system, it came up with this nice operating system, Windows NT, which was originally designed for x86 or Intel CPUs. Now, but at the same time, we had talked about these alpha processors, which when we talked about TAC TLBs, right? These alpha processors were very popular in the server environments, and Microsoft wanted their Windows NT operating system to be able to run on alpha processors. So what they did was they ported the Windows NT OS to alpha ISA so that Windows NT OS could run on alpha ISA. But there was only one problem. If you have an OS that runs on a specific hardware platform, but if there are no applications that run on that hardware platform, then it's no good, right? So, so all their applications, which were developed by people all over the world, they were all compiled for x86 platform, for Intel CPUs. And so if you just ran those applications on the alpha platform, what would happen? Windows NT would provide them the same system calls, but the user ISA part would be different. It would be alpha instructions. So whereas these applications are executing x86 instructions. So to do this to solve the user ISA mismatch, they wrote a runtime, which they called it Digital FX32 emulator. And what they did was, as the application was running, it would take every single user ISA instruction and convert it to the alpha user ISA instruction, right? So it was doing an emulation for individual processes. And that way all existing applications for Windows could run on the new platform. Okay, so there's a question from Gaurav. Some of the processors have an option enabled hardware-assisted virtualization. How does it work if guest OS is kind of virtualized from hardware? We will talk about this in system virtual machines, where we'll go to next, right? So, and so that's for a system virtual machine topic. I'll come back to this and we'll talk about how Intel VTD, how Intel VTX and VTD work. But for now, we're going to focus on process virtual machine. Is that okay? All right. So then there's another category of process VMs called same ISA binary optimizers. These are here we are again running process VMs where we are virtualizing the ABI, but the goal is not to do emulation. So in the previous case, we were converting from one ISA to another, but here the process has the same ISA as the hardware. So the goal of a runtime here is to do some optimization. For example, some runtimes would try to detect if there are memory leaks in your program, right? So somebody wrote a buggy program and then you have to run it, but then if you want to see if there are memory leaks or if there are any buffer overflows going on, or you might want to make it faster. Maybe the underlying hardware has certain optimizations that the application is not using. So you could, change the binary as it's running so that it can make use of those extra optimizations, run faster or be more energy efficient and so on. So people were doing this code optimization, binary optimization for many years. But then later everyone realized, hey, we are actually writing process virtual machines. We are actually writing runtimes. They have already talked about Java virtual machines, but this specifically falls under a category called high-level language VMs. So what that means is that you run your application, you write your application and you compile it. So it compiles into an intermediate representation called the virtual ISA. So for Java virtual machines, this is called the bytecode, right? So there are no physical processors, CPUs you can buy that support bytecode natively. So what you have to do is you have to run your application with the JVM software, and the JVM software would completely virtualize the ABI. So it will take each instruction of the bytecode and convert them to the underlying system calls and the user ISA instructions. So the Java virtual machine is platform dependent. Why would you want to do something like this? It's mainly for portability. So you can write an application against the bytecode, then you can take it to any physical machine, and hopefully the physical machine has Java virtual machine installed in it. So the Java virtual machine itself knows the details of the hardware, so you don't have to change your application. So your application is completely portable. You can run it on an x86 platform, then move it to an ARM processor or PowerPC processor, and it will just work as long as the hardware has a JVM installed in there. Okay. So, and likewise, the Sun Microsystems proposed JVM, and then Microsoft came up with its own version of that called CLI, and both of them have the same purpose. They're both high-level language VMs. Okay, any other questions so far? All right. So let's go to the next topic. So one thing I forgot to mention, I apologize. So we're going back here. Under emulators, there is an important distinction. There are two categories of emulators. Okay, so there are interpreters and there are dynamic binary translators. So interpreters are they both do the same thing. They convert instructions from one ISA to another ISA. Interpreters are slower. They would look at the source instructions and they would take one instruction, they would interpret it, convert it to the host ISA, and they will execute it. So they will basically go through this fetch, decode, and emulate or execute operation again and again. So, and then they would, once they do that for one instruction, they'll go to the next instruction, fetch, decode, emulate, fetch, decode, emulate. Okay. So they don't remember anything about what they've already done, so that if they encounter the same instruction again, they would do the fetch, decode, emulate cycle all over again. So interpreters are very simple to write, but they're also very inefficient. For example, if you have a for loop that's going to execute 1,000,000 times, then a simple interpreter would do this fetch, decode, execute cycle 1,000,000 times for that for loop, right? Which is kind of a waste of effort because you've already emulated it, fetched and decoded it once, so why are you going through that again, right? So dynamic binary translators are faster. They have many optimizations to speed up the emulation process. So dynamic binary translators will look at a block of code, and then they would decode and emulate the whole block of code once, and they would keep the translated result somewhere in memory. They'll remember that I have already translated this block of code, so I don't need to do it again. So next time you encounter the same block of code, you already have done the work before, you can reuse that emulated result, right? And you can reuse those instructions. So dynamic binary translators are much faster. And if there's significant locality in your instructions, you can get almost near native speeds with these. But then they're also more complex. So and there are various optimization strategies you can use to improve the performance of dynamic binary translation. Okay, So, and we will come back, we will also reuse this idea of emulation later in system virtual machines. Okay, so this brings us to the next topic, which is system virtual machines. And here we will first start from a high-level classification of system VMs, and then we'll go deeper into how individual resources are virtualized. So as we discussed earlier, system virtual machines need a special virtualization software, which is called the hypervisor. So in this picture here, you would see there's the hardware, which includes CPU, memory, and I/O. And then there is a layer of software called the hypervisor, which runs on this hardware and it directly controls the hardware. So what that means is that the hardware memory allocation or CPU assignment, CPU scheduling, or I/O operations, they are directly under hypervisor's control. Okay, so just like a traditional operating system completely controls the hardware, similarly, a hypervisor completely controls the hardware. Now, then once the hypervisor boots up, let's say that hypervisor is the first one boots up. Then once it boots up, then it can start many virtual machines. So in this case, we have started 3 virtual machines. The first VM runs guest OS 1 and its applications. The second VM runs guest OS 1, which then runs its applications and so on. Okay, so these 3 operating systems, they are running side by side. It's not like one or the other. They are all running concurrently and possibly sharing the underlying hardware. So you can think of hypervisor as an operating system for operating systems. So it's an operating system for guest OS 1, guest OS 2, and guest OS 3 in this picture. All right. So then you can ask, well, then what is the difference of a hypervisor from a traditional OS? The traditional OS also do the same thing. They control the hardware and then they run processes, right? So why can't we just think of these 3 VMs as just processes? I mean, why is hypervisor so special? Well, it's kind of true that hypervisors largely do the same things that traditional operating systems do. But there is one important difference, which is that hypervisors try to stay transparent or invisible, right? So ideally, you don't want the hypervisor to be visible. Like when you guys were doing assignment 2 using the CSVB, using the virtual machine infrastructure, right? If you had just used the SSH interface, you would feel like you're logging into your own machine. You didn't realize that you didn't have to interact with the hypervisor. You weren't aware that there was a hypervisor. Like sometimes when your machine would hang because your module was buggy, then you would have to go to the console and then you would reboot. But that's usually an administrator's job, right? The normal VMs users are not responsible for that. So likewise, so the goal of a hypervisor is to remain as transparent as possible. So what that means is that to pretend to provide, to pretend to these operating systems as if they're running on real machines. So the interface, the ISA interface seen by each VM looks almost identical to the underlying hardware, right? And what that means is that in order to hide, you have to let these guest operating systems do whatever they traditionally do, like however they traditionally manipulate the underlying hardware. But instead of manipulating the real hardware, they're going to manipulate a virtual hardware that's provided by the hypervisor. So each guest OS gets a bunch of virtual CPUs, some virtualized view of physical memory, and virtual I/O devices. And they do all their operations on this virtual CPU, virtual memory, and virtual I/O devices. And the hypervisor would trap and emulate the operations of the guest OS. So this trap and emulate behavior is a key thing, key property that distinguishes a hypervisor from traditional OSs, right? So because hypervisor wants to hide itself, it would intercept the privileged operations that are performed by the guest operating systems and then emulate them on the real hardware. So again, I've been using the term guest OS. Guest OS usually means an operating system that's running inside a virtual machine versus a native OS or a host OS that runs directly on the hardware. Okay, so there are lots of new terminologies being introduced. You know, just feel free to stop me if I don't explain anything properly. Any questions so far? All right. So, so the key takeaway from this slide is that, you know, hypervisors need to be transparent. Okay, so can you reiterate the importance of hypervisor again? Yep, sure. So the key takeaway is that the hypervisors want to be transparent. So like traditional operating systems, they do CPU scheduling, memory management, IO control, right? And then they do multiplexing. But the difference is that unlike traditional operating systems, the traditional operating systems make themselves visible. How do they make themselves visible? They provide system calls to applications. So applications, for example, they want to open a file, they will call open system call. What does that mean? Applications know there's an OS underneath, and if I make an open system call, OS will do something for me, right? Here, the guest OS may not know there is a hypervisor under there. It will think I'm running on my own machine, but actually it's running within a virtualized hardware. So the hypervisor's job would be to intercept those operations that the guest OS does, these privileged instructions that the guest OS executes, and then emulate them on the real hardware. So, or the hypervisor has to intercept or trap the privileged instructions and emulate them on the underlying hardware. Okay, so this is what adds additional overheads in hypervisor. So because normally these privileged instructions from the OS would directly execute on the hardware, but now hypervisor catches them in between and then takes an equivalent set of operations on the underlying hardware, right? So that trap and emulate operation, it adds extra overhead, but it also enables hypervisor to stay transparent. Okay, is that clear? All right. So now, just like we had different types of word process VMs, we have different types of hypervisors. You know, depending on you know, what kind of performance versus functionality you want, you can have different designs for hypervisors. So very imaginatively, you know, people name them as type 1 hypervisors and type 2 hypervisors, right? And there are things that are in between type 1 and type 2. So type 1 hypervisors or classical virtual machines are the types that were originally conceived, especially in the original IBM mainframe systems. So the idea there was that you would have the hypervisor or the VMM. Another name for hypervisor is VMM, or virtual machine monitor. So this hypervisor would boot up when you power on the machine. The first software that boots up will be the hypervisor. Just like for a normal OS, the first software that boots up is a normal OS, right? But in a virtualized system, the first software that boots up is a hypervisor. Then once the hypervisor boots up and, you know, establishes control over the hardware, then it can start virtual machines, individual VMs that can run side by side. So these are you know, classical virtual machines or classical system VMs that are running on top of a classical hypervisor. So what is so special about this hypervisor? Well, because it's the first software that boots up, it needs to know how to talk to the hardware, right? So what that means is if you have a specific CPU type, it needs to know all the details of the CPU type. If it are specific network cards or hard disk, it needs to know how to talk to those disk controllers. So it needs all the device drivers and all the architecture specific code needed to talk to the underlying hardware. So it has to be self-sufficient, okay? So if you're developing a hypervisor from scratch and you know what type of hardware is going to run on, then this is a great option, right? So you're willing to invest the effort to write a hypervisor from scratch, then you can optimize your hypervisor to run you know, most efficiently on the hardware, And to do this emulation, trap and emulate operation very efficiently. So whenever any guest OS does some privileged operation, you can trap and emulate it in the most efficient manner. Okay, so the original VMware ESX server, so VMware had different variants of their hypervisor. One was meant for desktop environments, another for server environments. So the ESX server hypervisor was their environment for virtual hypervisor for the server environments. And that was a type 1 hypervisor because it was written from scratch to run on specific type of hardware. And they would specify to get the best performance, like you have to buy this type of CPU and this type of IO devices, and then you can run. So the your assignment 2 VMs were running on VMware ESX server. It was a classical VM type 1 running on a type 1 hypervisor. Right? And likewise, some people claim that KVM is also a classical type 1 hypervisor, but you can kind of, there is debate whether you will call them type 1 or type 2. Okay, so you're not going to resolve that debate here right now, but some resources on the internet would say that this is type 1. Okay, although there are equally good arguments to say that it's type 2. Okay, any questions so far? What's type 1 hypervisor? All right. Let's go to the other one, type 2 hypervisor. Okay, so let's say you want to write your own hypervisor, but you don't have the patience to develop one from scratch, meaning that you don't have the patience to write all the device drivers and all the hardware dependent parts. Okay, so what can you do? Well, you can say, well, there are all these operating systems already out there, like Linux and Windows, that already know how to talk to the hardware, right? They already have all the device drivers you can think of in the whole world. So anyone develops a new hardware, they would first write device drivers for Windows and Linux and Mac and so on, right? So their hardware can be used with these devices. So why don't I use existing operating systems and then build my hypervisor into them? Okay, so this is called a type 2 hypervisor or a hosted virtual machine. So what that means is that you create a VM within the environment of an existing operating system. So for example, in this picture, you have an x86 hardware, x86 CPU, and you take an existing operating system like Linux, and you boot up Linux on top of the existing hardware, right? So a traditional operating system is running on existing hardware. And on Linux, you can have native applications, means you're running regular applications without any virtualization, processes, regular processes, right? But then you also write this special piece of software called the VMM or the hypervisor, which would partly run in user space and partly run in the kernel. Okay, so what you would do is you would write a kernel module and insert it into Linux, just like you wrote a kernel module in assignment 2. You would write a kernel module, which is actually a hypervisor, and you would insert it into Linux. And once it's in Linux, once you insert the module, it has full privileges of the OS. It can do anything it wants, right? A module, you know, you have to, that's why I say you have to be careful with what you do in a module, because module has full privileges of the underlying OS. So this particular module would then take over the host OS. It would take over CPU scheduling, memory management, you know, IO scheduling, whatever it needs to take over, right? And then using that, using those privileges, it can then run virtual machines, like just like classical type 1 case. So here there will be some user level helper software that would talk to the kernel module, and they would together create an execution environment within which a VM can run. So here the VM runs Windows operating system with Windows applications, right? So this is called a hosted VM because you are getting the help of a traditional OS, but then you're using it to to benefit from existing device drivers, right? So what does the hypervisor need Linux for? It needs Linux for its memory management capabilities. It needs it for talking to network card or hard disk and so on. So the hypervisor doesn't need to implement all these pre-existing functionalities. It can let Linux do all that stuff. But then as far as control of the CPU privileges is concerned, control of any critical functionality related to the virtual machines is concerned, trap and emulate capability, all that would go through this kernel module hypervisor that you have inserted. Right? The hypervisor is still the most important software now, although it was inserted as a kernel module. So because the host OS is not optimized for virtual machines, so this may not be the most efficient way to do it. For example, if you're going through the Linux file system to store the virtual image of your virtual disk image of your virtual machine, right? So then the file system may be inefficiently implemented. So whatever inefficiencies exist in native Linux, those will be inherited and transferred over to the virtual machines. So it's not as optimized as a classical type 1 hypervisor. But if you want a quick and dirty way of starting up your VMs, this is a fairly decent way to go about it. Okay. Any questions so far? The difference between type 1 and type 2 hypervisors? Okay, so question is from Anurag, Professor, in type 2, if hypervisor takes control, then does it also run applications of host OS? No, so you don't have to, right? So if hypervisor takes control, if your primary job is to run virtual machines, then you can leave all the other jobs to the original host OS. So the host OS still controls the native applications and everything. But whenever there's anything to do with the virtual machine, then in that case, the hypervisor would step in. So you would intercept only take control of only the bare minimum functionalities that you need. Of course, if a hypervisor wants to take over the native applications, also nothing stopping it from doing that. But why would you want to? Okay. All right. So then there is another type of virtualization, which is called para-virtualized VMs or para-virtualized virtual machines. Okay. So what we are, so this can be both type 1 and type 2, right? So there's the orthogonal to type 1 and type 2. So what does it mean? So the problem that para-virtualized VMs are solving is that if we go back to the original picture that we saw here, we said that if hypervisor was supposed to be completely transparent or invisible to the guest OS. So if to be invisible, they have to do a lot of these trap and emulate operations, or they have to intercept these privileged instructions and emulate them, right? So that the more you have to intercept and emulate, the more expensive the overhead of the system is going to be. The hypervisor would have to run more often, and it would reduce the performance of the applications within the VM, right? So in para-virtualized VMs case, people said, well, how can we reduce this trap and emulate cost? Okay, so well, the primary reason you have this trap and emulate cost is that hypervisor wants to be completely transparent or invisible. But what if you remove that requirement? Like, I want a hypervisor, but I don't want it to be completely invisible. Like a traditional OS is not invisible. It provides system calls, right? So what if a hypervisor could provide something, an equivalent of system calls to the guest OS? Okay. What if hypervisor could let the guest OS know it's there and they can use its capabilities through some special interface? So hypervisors can then provide an interface called hypercalls to the guest OS. Just like operating systems provide system calls to processes, hypervisors can provide hypercalls to guest OS. And by doing that, hypervisors can provide an easier interface for the guest operating systems to make use of their virtualized hardware, a more efficient interface. But of course, you're giving up on transparency. So once you have guest OSs that use hypercalls to access the hypervisor services, then guest OSs know there's a hypervisor, right? So you're given up on transparency, you're given up on being invisible. So you can gain additional performance by giving up transparency, right? But you don't have to give up transparency completely. Only for very expensive trap and emulate operations, you can provide hypercalls. But for all the other operations, you can stick to the traditional trap and emulate model. So, so by compromising on some of the key properties, transparency properties of a hypervisor using hypercall mechanisms, you can create para-virtualized VMs. Para-virtualized meaning that we are modifying the guest's operating systems to be aware of the hypervisor so that they can more efficiently perform some operations that would otherwise be very expensive. Okay, so this is mainly a performance improvement technique, and one of the first para-virtualized operating systems was para-virtualized hypervisors was the Zen hypervisor, which came out around the same time as VMware. So VMware hypervisors were fully virtualized, fully transparent, whereas Zen was fully para-virtualized, and they would modify the guest OS significantly in order to get great performance. So VMware's hypervisors would run VMs with 70% efficiency, and Zen would do it with 95% efficiency because the guest OS was so highly modified. But Zen was not, transparent. So it turned out that in the long term, actually, VMware grabbed a bigger share of the market than Zen. Okay, but later down the line, both Zen, the playing field got leveled because Intel came up with hardware level support for virtualization, and that way both Zen and VMware could use hardware support and they could match their performance. All right, so so that's the key thing. So now when you look at hypervisors, either Zen or VMware, they'll both use some aspects of para-virtualization and some aspects of full virtualization. So they'll try to be as fully virtualized as possible, but where, for example, IO device accesses, like when you're accessing virtual disk or virtual network card, then you would use a para-virtualized version of the model for corresponding hardware devices. Okay. Does this make sense? Any questions so far? Okay. So, so this brings us to another category of virtual machines called whole system virtual machines. And this is very interesting. It's kind of a combination of process VMs and system VMs, but it's really a system VM which uses some features of process VM. So what's the history behind it? So long back, Apple's computers, Mac OS, used to run on a special processor called PowerPC, which was manufactured by IBM. And PowerPC had a different ISA. And Mac OS would use PowerPCs, and they had their Mac OS was fully optimized to run on PowerPC. It was very energy efficient, and battery power savings and all was very important for Apple, right? But Windows was very popular because it had a lot of useful apps that many users wanted, especially things like Microsoft Word and so on. So the entire Office suite, right? And Apple didn't have an equivalent killer apps. So Apple and Microsoft collaborated, and then they developed this special virtualization software called Virtual PC. Okay, so what did Virtual PC do? It would virtualize the ABI provided by the Mac OS, the system call and user ISA interface provided by Mac OS. Mac OS and PowerPC platforms. And then it would provide an x86 ISA. So remember that PowerPC ISA is different from x86 ISA, right? And all the Windows applications were designed to run against the Windows ABI, which was, and the Windows OS was also written primarily for x86. So, so they were basically translating the Mac OS ABI into x86 ISA. So they were emulating x86 ISA on top of Mac OS ABI. And by doing this, you could run an entire Windows OS and all Windows applications within this virtual PC environment. Okay, which is pretty cool. So by doing this, you can get the benefit of all the Windows applications within a VM on a Mac OS, which are running side by side with Mac applications. It's a pretty cool thing. So later, of course, system virtual machine technology became more mature, and Mac itself started providing greater support for system virtual machines, and you can now run Windows VMs on Mac OS, if you have the correct virtualization software installed. Okay. Any questions on this? All right. So, and this brings us to another interesting use case called co-design VMs. So what is the story here? There was a company called Transmeta Crusoe long back, and now I think they've closed now, but it was a startup company, and they were looking at embedded system or low power system space, and they were trying to design processors that could work in this low power system space. So they came up with a processor architecture that used something called VLIW, or very large instruction word ISA. Okay, and of course this is different from x86 ISA. So they had this processor that was very power efficient, and it had certain parallelism capabilities supported by VLIW architecture. But then the whole world was using x86 ISA. All the applications were written using x86 ISA. So if they wanted people to buy their hardware, then they would have to support x86 applications. So what did they do? They wrote a hypervisor for their hardware that would take x86 applications and run them on VLIW. But that hypervisor had to run at hardware speed. It couldn't just be software. So they wrote a hardware-based hypervisor, or rather a firmware that was closely designed to their hardware, which would do this emulation from x86 to VLIW instructions, right? So, and it would be very closely, because the hypervisor itself is very closely designed with the hardware, it would have great performance. So it was co-designed with the hardware. The hypervisor was co-designed with the hardware. So your VMs would run normal x86 operating systems and x86 applications, but then internally for every instruction would go through this co-designed hypervisor, which is Transmeta Crusoe's own hypervisor, which would then convert these instructions to VLIW, and then they could use this hardware. So I don't know what happened to their technology, but at least in Smith and Nayer's book, they use this as an example to show, how hypervisor capabilities can be built into the hardware itself. Okay, and there's again increased interest, I think, in building hardware capabilities in co-designed VMs. And many times people are saying, why are we running hypervisors as software? We should actually be building it into the hardware itself. So it's kind of a broad taxonomy of the various types of VMs we have covered so far. We've looked at process VMs, system VMs. In one case, we are virtualizing the ABI. In the other case, we are virtualizing the ISA. And just by virtualizing different interfaces, we get two different types of VMs. And within that, we have looked at same ISA VMs and different ISA VMs in each of the categories. So if you look at the same ISA process VMs, and within that you have regular multi-program systems, processes, and then things like dynamic binary optimizers, where the source ISA and target ISA are the same, but you're doing some optimizations like finding memory leaks or running the programs faster and so forth. And there are different ISA process VMs. We have emulators, which can be interpreters or dynamic binary translators. And well, we also looked at a special class of these different ISA VM called high-level language VMs, such as Java virtual machines. Okay. Then under system VMs, we have again looked at same ISA and different ISA VMs. There are classical type 1 VMs, there are type 2 VMs or hosted VMs, and then there are para-virtualized VMs. There's something, so this hardware virtual machines, I've put it in there, but there was briefly a period where, when VMs can directly access, are allowed to directly access hardware devices, IO devices. Now it's called pass-through devices, but earlier for a brief period of time, they were called hardware virtual machines. I'm not sure that, I don't think that's a common terminology now. So, so just ignore that term. Okay, so it's not widespread use. Under different ISA system VMs, we talked about things like virtual PC, where they're whole system VMs, and also things like Transmeta Crusoe, which are co-designed VMs. Okay, and I think this is going to be the final slide I'll cover today. So you can have, with all these levels of virtualization, right? You can have different, very interesting use cases. For example, you may have a hardware that's based on Transmeta Crusoe's VLIW architecture, and then you can run their hypervisor and hardware, which they used to call code morphing hypervisor, and then within that you could run a VM in that environment, which runs Windows applications, right? So Windows OS with Windows execution environment. But in that Windows environment, you can install VMware's, say, desktop client, and within that VMware desktop client, you create a VM within a VM, right, where you're running Linux operating system. And within the Linux operating system, you could fire up a Java application. Like you could fire up a browser within which you're running a Java applet or something, and that's doing all the which is running bytecode, which is translated into by the JVM or interpreted by the JVM. So the net result is you're running Java applications on a Crusoe VLIW, but going through these multiple hops. So why would anyone want to do it? Of course, it would probably be very, very, very slow, because there's so many levels of interaction. But something you can do something like that is kind of cool. Okay. So any questions? Any comments? Any doubts? Utilizing individual resources.